All right, so let's take a look at reflux. So reflux is often considered in the context of esterification. And so remember, esterification is the reaction where you take an alcohol plus an alkanoic acid or carboxylic acid and react to get your ester and water.
Yep.
Now, remember, this reaction doesn't actually, proceed to completion. So you need to use equilibrium arrows.
Yep.
And, there's a few details that we'll fill in a bit later. But remember, your alcohol is basically some sort of OH.
Yeah.
It will react with an alkanoic acid, which is some sort of, R prime. Then you've got some sort of COOH group. And then you're going to get your ester, which basically takes the R, and then it's going to basically link, to an O. So it's going to link to this sort of O here, and then this sort of C double bond O. And then this is then going to link to an R prime. So this is the green part, and this is the blue part. And then you're going to then, of course, have water left over.
Yeah.
So remember, pay attention to the functional groups. This is what makes it the alcohol. This is what makes it the carboxylic acid. And this here is what makes it the ester.
Yeah.
And just remember with esterification, apart from the sort of functional groups that are important, esters, of course, are used for flavoring and usually have some sort of pleasant smell or pleasant odors. And, so you're used to using them for sort of flavoring and sort of, smells and perfumes and things like that.
Yeah.
And so a typical example of esterification, take some sort of alcohol. So let's go with, say, ethanol. And let's take some sort of alkanoic acid, let's say propanoic acid. And then they'll react. Now, ethanol is, of course, your primary alcohol like so. And then it will react with propanoic acid. And this time I'll put the COOH on the left. And essentially, these are going to sort of react. And so essentially you'll end up with your, ethyl, which is this section. And then it's going to be linked to the propanoate. Let's make this a little bit smaller. Okay. So I'm going to get and of course you'll get your H2O. So that's why you'll end up with your ethyl. So this is your ethyl, and this is your propanoate. And that's how you name your esters as well. So your ester in this case will be ethyl propanoate.
Yeah.
Plus water. Now, basically that's esterification. But of course, we note that it's not a complete reaction. And in fact, if you just mix alcohol and alkanoic acids together, it doesn't really happen, all right?
Yep.
So the reaction is firstly incomplete and also does not really, proceed at room temperature. So if you want it to happen, what do we need to then do then, if we wanted to help it along?
Provide heat.
Right. So to aid in increasing rate, we would need to heat it up. Now, keep in mind what you've got. You've got alcohol plus alkanoic acid. And you're now providing heat. And of course, now potentially it's going to react to form your ester plus your water. Now, the way a lot of students think about this, certainly initially, is they'll just go, okay, you've got a beaker, you dump in your alcohol plus your alkanoic acid. And, you put it on a Bunsen burner and off you go. So that's basically how a lot of students think about this to start with. But why is that problematic?
Because alcohol has a low boiling point.
So,
well, escape from the beaker.
so there are quite a few problems. One of them is the fact that, well, alcohol, and in fact, not just the alcohol actually, but, depending on the lens, but these things are all potentially going to evaporate.
Yeah.
Including water, if, depend on how much you're heating. And, they're going to evaporate and, you'll have nothing left, right?
Yeah.
What else is a problem?
They're flammable.
Yeah, it's a pretty big problem, right? Certainly alcohol is flammable. So if you've got it floating around, it's, might cause a fire hazard. Anything else?
I'm not sure.
So there are a few concerns. You've already listed some. So if we proceed with it that way, there are sort of what problems we may come across? Well, firstly, we note that the reactants and products are volatile. They're both volatile and potentially toxic. So if heated, they are volatile, so therefore they'll evaporate. Now that can cause multiple problems. Number one, that could be a toxicity issue, right? Because you don't want to breathe in alcohol necessarily. Certainly not for prolonged periods at high concentrations, right? So, that could be an issue with toxicity in terms of alcohol. As an example, what about other than alcohol? What else do we have that might be an issue?
Acid.
Right. You don't want acid in the air either. So, you might also have issue with sort of, vaporized acid. And that's obviously going to be an issue in terms of your skin, right?
Yep.
And eyes in particular. So that's another problem, right? You also don't want to breathe it in, so your lungs, right? All right. So that's a problem potentially. And then, of course, you've got the issue that you mentioned earlier that, you could just, have these leaving. So in general, if it's evaporating, loss of reactants and products. So therefore, lowered yield, it's all gone. It's really not what you want.
Yeah.
And, you've now got alcohol being sort of vaporized around. And that's another issue that you mentioned earlier. And that's basically alcohol is flammable, and therefore you now have a fire hazard or possibly explosion, depending on the circumstances. Does that make sense?
Yeah.
So there are quite a few risks here. So how do we manage these risks?
With the reflux?
Well, obviously, that's true, and that's where we're heading. But let's start basic because, I think it's a good opportunity to also talk about general experimental techniques as well. How do you try to, reduce the issue with sort of your skin, eyes, lungs,
With protection?
Yeah, so basically for skin, your lab coat, gloves, so on. Your eyes would be your goggles. Your lungs would be, well, what will we do there?
Uh, 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 the like open area.
Yep, so fume covered and good ventilation. All right.
Yeah.
Toxicity, again, with this, basically, same thing, good ventilation, open area, open windows, and so on.
Yeah.
Open windows, ventilation, etc. How do you deal with a fire hazard?
Fire. We use a hot water bath.
So that's part of it. But just again, starting with the basics.
We don't use fire.
Yeah, well, yeah, but to prevent it happening, if it does occur, have a fire extinguisher, etc. on hand. All right.
Yeah.
But of course, we still need to heat it, and so, as you said, this still causes an issue with having a fire. So what we want to do is we also want to avoid, if possible, certainly not close a naked flame. And that is where, indeed, we use indirect heat. So your indirect heating is now provided with two options. So basically, instead of having, so what is wrong and not really done is you certainly don't have your sort of reaction flask, directly heated by fire, like a Bunsen burner. That's not done because, it's bad for the glass and all that kind of thing. But you've got two options. You either use, a water bath, as you mentioned. So we basically do heat it, but one of the options where we heat it is to use a water bath. So basically that just means you submerge it in water. And this helps because, of course, if you heat this with a Bunsen burner, well, this might be quite hot, but this water at best will be 100 degrees.
Yeah.
And so it's cooler temperature, and it will also promote even heating. So because rather than this getting very hot and this not so hot, this will make all of this area fairly even.
Yeah.
Right? So option one is a water bath. And, it increases the distance between these things because it's got to go all the way up there and the flame. So it's, quite far away by the time it escapes. This is before we even put in the other stuff that we're about to put in. So, it's going to be quite safe. But an even safer option is basically just to use a flask warmer.
Yeah.
And so, or flask heater, where basically you literally just, it's an electronic device. So you just literally have the flask and just place it into a heater. Both options would basically be considered fine. and there is no flame in this option. All right. And so that's one part of reflux. The reflux is you're going to need to provide heat in some way, either option 1 or option 2. And going forward, I'm just going to, say heat is provided. I'm not going to talk about how, because it doesn't really matter which way you're going. So getting to reflux, what that we really need to do now is we're going to have our flask. And we're going to provide heat. Possibly in a water bath, possibly with a flask warmer. Now, what is in our mixture? How do we, what do we want to get it to react?
Alcohol acid, that's and concentrated sulfuric acid.
Right. So we're going to have alcohol and carboxylic acid. So in our mixture, we've got alcohol, carboxylic acid. Now, as we said, this is an equilibrium reaction, which means you want to sort of heat it up to help it along. And one way to help it along is to add in a concentrated sulfuric acid as a catalyst.
Yeah.
And we perform this under reflux. Now, when this reacts, you're going to produce an ester. And water. So these are your products.
Yep.
But, I mean, do we have anything else here?
Acid, sulfuric acid, no.
Outside of these, do we have anything else in here? So you do need to add something else. And these are basically just your boiling chips. All right. So your flask will have some solids in it, which is just your boiling chips.
Yeah.
It's going to have your catalyst, your concentrated sulfuric acid, your alcohol, your carboxylic acid, your ester, and your water.
What are the boiling chips for?
So, yep. So some quick things. So purpose of the boiling chips. Essentially, if you get asked this, it'll be like a 1-mark question. Essentially, it's, just basically memorize for now, to promote even heating and prevent bumping by providing nucleation sites. So, you can probably get away even with less. To promote even heating is often a very simple answer. Promoting even heating prevents something called bumping. And the way it does that is through providing nucleation sites. Might not be necessary to go into the, explanation behind all of that, certainly today. But that's basically the purpose behind the boiling chips.
Yep.
Okay. Now, reflux means that you heat it, but you need to add a condenser on top.
Yep.
So we're going to add the condenser. Remember, cold water in the bottom, hot water out. Okay. And that then ties into your flask, which is being heated. Remember, your flask has a reaction mixture, including boiling chips, as aforementioned mentioned, plus your reaction mixture. Now, this reaction mixture, of course, this reaction mixture obviously includes everything we said earlier. And the whole purpose of this condenser here, of course, is as you provide heat, of course, these things being volatile, they will evaporate, and then they'll come here, pass through the condenser, and so they will condense and then fall back down.
Yeah.
And so the purpose of this is therefore to both, recondense the vapors as they rise. And this therefore basically, prevents the escape of vapors. And that's both reactants and products. And that is helpful both in terms of the yield perspective, but also in terms of all the safety things that we talked about as well. Now, therefore, after some time, give it some time, this will now provide, and given it's in equilibrium, it will include your reactants, which is your alcohol, your carboxylic acid. It will also have your catalyst, which is your sulfuric acid. It will also have your ester and water. And so you've got all this mixture over here. Now, you might want to also, when you prevent the escape of vapors, how do you guarantee that, the vapors don't escape? Well, firstly, you don't guarantee it. You're just trying to minimize it. So one thing that's also important is that you don't close off this top. Because if you close it off, one thing that could happen, is that the pressure builds up in the middle and causes the glass to shatter.
Yeah.
Now, hopefully nothing too bad, but basically you want to avoid that. And so, if it wants to escape, you just let it escape. And you try to minimize the amount that escape by controlling basically your heating rate and your, water flow rate. So basically when you're doing the experiment, you analyze and keep an eye on the vapors. If you see that this entire section is, all vaporizing, then you're heating too much and it's not cold enough, right? So basically you should see vapors condense at the bottom, and the top part basically shouldn't see any vapors, certainly not to the eye, because, you should get the majority of vapors condensing, before it gets to the top.
Yeah.
And you either reduce the amount of heat or increase the flow rate of water, either or, to achieve that. All right. So there's a few things we might also want to talk about. We talked about the role of the boiling chips, but we might also want to talk about the role of the sulfuric acid. Now, why do we have the sulfuric acid? We said to act as a catalyst. And remember what that means, that lowers the EA. And if you're interested in how it lowers the EA, then you can look up what's called the Fischer esterification process. We won't get into that here. But basically, essentially, it acts as a, homogeneous catalyst. It's a, it provides intermediate steps, all right? It's not a surface catalyst, it's a, intermediary kind of catalyst. But is there any other reason that we would add sulfuric acid?
Acidic condition, something?
It's also to act as a dehydrating agent. Okay. So concentrated sulfuric acid, and only concentrated sulfuric acid does this compared to, dilute, that is. It acts as a dehydrating agent. So think of it like it sucks water, all right?
Yeah.
And why would that help?
To get rid of the OH.
And why did that help?
For the reaction to occur faster.
not so much occur faster.
The rate to increase.
So it's a dehydrating agent, right?
Yeah.
So if it takes away the water,
Yeah.
then it will essentially shift the equilibrium to the right, yeah.
Oh.
So it will essentially, you know, ultimately cause the system to shift right.
Yeah.
And increase yield. Now, you know, technically the reason for why that happens is the reasons that we outlined earlier in terms of think of it like the aqueous solution of those things, right? But yeah, basically that's the idea. Okay, it's going to increase, it was going to shift to the right.
Yeah.
And that's basically your esterification and your reflux. You know, after this, you might want to consider how you separate this out. But that this basically what we've covered so far is basically your esterification and your reflux.
Yeah.
Yeah.